Okay, this is another two-part problem. It reads, my car has an internal volume of 2,600 liters. If the sun heats my car from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius, what will the pressure inside my car be? Assume the pressure was initially 760 millimeters of mercury. 760 millimeters of mercury, that is 1 atmosphere, so this is a standard pressure. That's why we can assume that this is what it was. Part B says, how many moles of gas are in my car? Okay, so let's get started. First things first, we always write our knowns and our unknowns, and we're going to do this just for part 1. And then we'll go back and make a new chart for part 2. Okay. Knowns. We know that volume is 2,600 liters. We know that our first temperature is 20 degrees Celsius. We know that our final temperature, T2, is 55 degrees Celsius. And we're looking for pressure. We're looking for second pressure, knowing that our first pressure, initial pressure, is 760 millimeters of mercury. And I don't think you can actually see the stuff that I'm writing right now. Hang on. What's that? Is that better? I bet it is. Okay. So, our volume of our car, 2,600 liters. We have a T1, a T2, a P1. We're looking for P2. We know from Gay-Lussac's law that P1 over T1 equals P2 over T2. If we can't remember Gay-Lussac's law, we could also start with a combined gas law. P1V1 over N1 T1 equals P1 P2 V2 over N2 T2. And we could cancel out the stuff that's constant. We have only one volume of our car. The volume of our car is not going to change, so these are constant. We don't know anything about moles of gas, but we know that's not going to change because nothing's coming in or out of the car, so those are constant. And we would end up with Gay-Lussac's law, which is what we're going to use. So we know we're looking for P2, so we can rearrange this equation, Gay-Lussac's law, so that we isolate the variable, get P2 by itself. We'll do that by multiplying both sides by T2, and we end up with P2 equals P1 T2 over T1. That's really messy. I'm going to rewrite that. P2 equals P1 T2 over T1. Sorry. Okay. So now we have our equation. All we have to do for part A, the only thing left is to plug it in. So for part A, we have P2 that we're looking for equals P1, 760 millimeters of mercury. T2 is 55 degrees Celsius. T1 is 20 degrees Celsius. Now I know in other problems I've gone ahead and converted everything to the same units as our gas law constant R. And I know I've told you that the first thing you should always do is convert your temperatures from Celsius to Kelvin. That is definitely true if you know you're going to be using R. If you don't know if you're going to be using R, then go ahead and convert them. If you know you're not going to need R, then you don't have to convert them. But if you're going to need R, you have to convert these things. Anyway, in this case, it doesn't actually matter because our Celsius is still going to cancel with our Celsius, and we'll still be left with millimeters of mercury, which is a unit of pressure. And it didn't ask us what unit to put our pressure in. It just asked for the value. So as long as we label it, it'll be okay. 760 times 55 divided by 20 is 2,090 millimeters of mercury. If we're going to use sig figs, significant figures, that would be 2100 millimeters of mercury. And that's our final answer for part A. So now for part B, we have to figure out how many moles of gas are in the car. We'll make a new knowns and unknowns chart. We now know a volume. We still know this. This was 2,600 liters. We know a initial temperature and a final temperature, 20 and 55. We know an initial pressure of 760. And we know a final pressure of 2,100 millimeters of mercury. What we do not know is our moles of our gas. So to find moles of our gas, we're going to have to use an equation that has N. We know the moles of our gas do not change. And because our moles of gas do not change, we don't want to use the combined gas law, P1V1 over N1T1 equals P2V2 over N2T2. Because if we use this, then our moles will cancel with each other because they're initially and finally the same. We don't want to use the combined gas law. Instead, we're going to use our friend, the ideal gas law, PV equals nRT, which means we can add another known up here, R equals 0.0821 liters atmospheres per mole Kelvin. So first we need to rearrange so that we're looking for N. Isolate the variable by dividing by both sides by RT. We get N equals PV over RT. So using the initial values, we'll see N equals P1, 760 millimeters of mercury, times V, 2,600 liters, over R, 0.0821 liters atmosphere per mole Kelvin, times our temperature, T1, was 20 degrees Celsius. And here we run into a problem because we never converted our units. We can't cancel Kelvin with degrees Celsius, and we can't cancel millimeters of mercury with atmospheres. So what we're going to have to do is convert quickly and put the other values back in. So 760 millimeters of mercury, as it turns out, is the same thing as 1 atmosphere. So we have 1 atmosphere to plug in as our pressure. We can come back up here and write that, 1 atmosphere. And for our temperature, we know that 20 degrees Celsius plus 273 equals 293 Kelvin. So we can plug that in here, 293 Kelvin. And now our Kelvin and our Kelvin cancel, our liters and our liters cancel, our atmospheres and our atmospheres cancel. We're left with 1 over mole, which is the same thing as 1 divided by 1 over mole, which is the same thing as 1 times mole over 1, which is a mole. So we know that we've plugged everything in right because we ended up with the right units. So when we multiply all of this out, 1 times 2,600 divided by 0.0821 divided by 293, we get 108.1 moles.